Hello everyone, and welcome to this focused lecture series designed to help you prepare for the NVIDIA Certified Professional Generative AI LLMs exam. We are starting right at the foundation with Module 1, LLM Architectures. Now, if you've looked at the exam blueprint, you might notice this module only carries about a 6% weight. However, don't let that number fool you. This module is the bedrock. If your understanding of these core concepts is shaky, advanced topics like optimization, quantization, and deployment simply won't make sense later on. Our goal today is to master these foundational structures so that you have a solid base for the rest of your study. Let's dive in. Let's establish our shared vocabulary. This pipeline you see on the screen is critical. Every LLM, no matter how complex, follows this general path during inference. We don't feed raw text directly into a neural network. First, the tokenizer breaks text into manageable pieces. Numbers, really. These numbers become embeddings, turning discrete tokens into dense, high-dimensional geometric vectors, where the mathematical processing happens. These vectors are then processed by layers of transformer blocks, which we'll discuss shortly to gather context. Finally, an output head turns that processed data back into a probability distribution to predict the very next token. Understand this flow, and you understand the entire inference lifecycle. So, that's the general pipeline. But not all transformers are built the same. Historically, the original transformer had two parts: an encoder to read and a decoder to write. Modern architectures often specialize. Looking at the left panel, encoder-only models like BERT are highly effective readers because they utilize bidirectional attention, which is looking at the whole sentence at once. They are superb at natural language understanding tasks like classification or named entity recognition. In the middle, we have decoder-only models like the GPT series. These are writers. They use a causal mask, meaning they can only see what came before the current token. This makes them the industry standard for text generation and chatbots. Finally, on the right, the full encoder-decoder, like T5. This is your classic sequence-to-sequence architecture. It is the ideal choice when your input and output are fundamentally different sequences, such as language translation or text summarization. As a reminder, the exam loves scenario-based questions, testing your ability to pick the right architecture for a specific task. Okay, let's pop the hood. Why did transformers replace previous architectures like RNNs? The answer is largely on this slide. That is, self-attention, which enables GPU parallelization. Unlike RNNs that process words sequentially, transformers process the entire sequence at once. But how does the model know which words relate to each other? And that's the magic of self-attention. Shown in Visual 1, it uses three matrices: query, key, and value. Think of it like a filing system. The query is what a token is currently looking for. The keys are the labels on the folders. The values are the actual information inside the folders. The model calculates a score by matching queries to keys to determine how much attention to pay to the corresponding values. And as visual 2 shows, we use multi-head attention. We run these processes in parallel, allowing different heads to focus on different aspects of language simultaneously. One head might look at syntax, another at semantics, giving the model a massive computational advantage. Okay, let's move back to data representation. As I mentioned earlier, models understand math, not English. Embeddings are where text turns into geometry. An embedding takes a discrete token and places it into a high-dimensional vector space. The crucial concept for the exam is that semantic similarity equals geometric proximity. As you can see in the visualization, words that mean similar things, like apple and orange, cluster together in this space. Furthermore, the relationships between words remain consistent. The vector distance and direction between king and queen is roughly the same as between man and woman. Why does this matter practically? Because you can programmatically extract these intermediate vectors. This is the foundation of retrieval augmented generation, RAG, and modern semantic search systems. We have processed the data. We understand the context. Now, how do we control how the model speaks? That is output sampling. The output head gives us probabilities for the next word. If you always just pick the single most likely word, called greedy decoding, your output can be repetitive and robotic. To make it human-like or creative, we sample from that distribution. Temperature is your main lever for creativity. A high temperature flattens the probability curve, making rare words more likely to be chosen, but also increases the risk of nonsense. A low temperature, on the other hand, makes the model conservative and deterministic. We also use top K and top P as guardrails. They essentially say, don't look at the entire dictionary. Only consider the top 50 words. That's top K. Or the smallest group of words that together account for 90% probability. Top P. Top P is also called nucleus sampling. Finally, we have beam search in Visual 3. This strategy is a bit different. Instead of just looking at the single best next word immediately, beam search keeps track of several promising sequences of words simultaneously. As the tree diagram shows, it explores multiple future paths at once, calculating cumulative probabilities and pruning the less likely paths along the way. It's computationally more expensive than greedy decoding, but it often results in more coherent overall sentences, especially for tasks like translation or summarization. Mastering these controls is your primary defense against hallucinations and is crucial for tuning model performance in production. All right, that covers the core theory for Module 1. Now, let's shift gears and apply this knowledge. We are going to walk through 5 exam-style scenario-based questions. For each one, I'll read the scenario, give you a moment to think, and we will reveal the correct answer and explain the logic. Okay, question 1. A startup is building a real-time language translation service for a live video conference platform. The system needs to take a continuous stream of spoken English and generate a corresponding stream of Spanish text with high accuracy and minimal latency. Which of the following architectures is best suited for this core translation task? Take a moment to look at the options. The correct answer is C, encoder-decoder, example T5. This is a classic sequence-to-sequence task. The input sequence, English, is fundamentally different from the output sequence, Spanish. The encoder-decoder architecture is specifically designed for this. The encoder processes the input context, and the decoder generates the target translation. While other models could attempt this, T5 is the most specialized tool for this specific job among the given choices. Question 2. Your team is developing a creative writing assistant that helps users generate short stories based on a prompt. You decide to use a large, pre-trained, decoder-only transformer model. What's the primary architectural characteristic of this model that makes it well suited for generative tasks, but less ideal for tasks requiring full bidirectional context, like sentiment analysis on a complete sentence? Look at the options regarding attention mechanisms. The correct answer is B. Its reliance on a causal or masked self-attention mechanism. Decoder-only models are excellent writers because they generate tokens autoregressively, that is, one at a time, looking backward. The causal mask enforces this by preventing the model from cheating and looking at future tokens. This same mechanism, however, prevents it from understanding the full bidirectional context of a completed sentence in a single pass, making it less ideal for natural language understanding tasks compared to an encoder, which sees the whole sentence instantly. An AI engineer is analyzing the attention weights of a transformer model to understand how it processes a given sentence. They are specifically looking at the scaled dot product attention calculation. In the context of the query, key, and value matrices, what's the primary role of the key matrix? Think back to our filing cabinet analogy. The correct answer is C. It serves as a set of descriptors or tags against which the query is matched to determine relevance. The query is what the model is currently focusing on. The value is the actual information context. The key acts as the descriptor or label that the query is matched against to decide how much attention to pay to that specific value. Question 4. A data scientist is exploring a pre-trained word embedding space. They perform vector arithmetic to find that the vector resulting from king minus man plus woman is closest to the vector for queen. What fundamental property of well-trained embeddings does this demonstrate? The correct answer is C, the linear substructure where consistent vector offsets represent semantic relationships. This classic example demonstrates that embeddings capture more than just clustering. They capture semantic relationships as consistent linear directions in 3D space. The direction and distance, representing the concept of royalty or gender, is consistent across different pairs of words. Okay, last question. You are deploying an LLM-based question answering system that retrieves information from a set of technical manuals. The priority is to provide the most factually accurate and deterministic answers possible, with minimal creativity or hallucination. Which sampling strategy would be most appropriate for this use case? Remember, we want facts, not creativity. Which option ensures that? The correct answer is B. Use greedy decoding, or a temperature of 0 or a top K of 1. To minimize hallucination and ensure maximum determinism for factual tasks, you want to eliminate randomness in the generation process. Greedy decoding always selects the single token with the highest probability at every step. High temperature or beam search introduces variance that's undesirable in this specific scenario. That concludes our review of Module 1 LLM Architecture. You should now have a solid grasp of the fundamental structures like encoders, decoders, the mechanics of self-attention, the geometry of embeddings, and how we control output via sampling. These concepts will serve as a foundation for the next module, where we will discuss prompt engineering. Thank you for watching.